Right? This is 9, right? So we did talk about the exam 1. So if you see the schedule, you see week of 23, right? So that's the one. So 23 gonna be Monday. So do I have on Monday? 23? This Monday. Is it okay? You're gonna have some time to review during the weekend? Probably gonna be helpful. Alright? Sounds good? Alright. So then what we're gonna do is we're gonna do exam on Monday, September 23. We're gonna do class revision on Friday before that, which is gonna be 20, right? So the whole class on 20 gonna be the revision. So I'm gonna post practice questions probably by tomorrow sometime. So you're gonna have more than a week to go through that and to practice it. Okay? Sounds good? All right. So with that, we're gonna continue chapter 3, right?
Professor,
Uh-huh.
so will the exam be up to chapter 3?
Exam gonna be chapter 2, 3, and 4.
Oh, and the next one.
So far 3 chapters. So we're gonna finish chapter 4 by Wednesday. Next Wednesday. Okay. It's not that long. Chapter 4 is gonna be kind of revision of Gen Chem. Student base. You have different theories like, right? So Arrhenius theory, Bronsted, Lewis theories. So we're gonna cover that.
Okay.
Okay? All right. So cover this, right? And also do this. So we're gonna continue from here. Alright. So for the cyclohexane, we have 2 different types of hydrogens there. Right? One type are the 6 hydrogens, which gonna be axial. If you see from the axis of the ring, right? So you have cyclohexane like this one. So you're gonna have, if you see this way, right? So you're gonna have this one, this one, this one, this one, this one, which are perpendicular to the plane of the ring. So these are axial. Okay? And then the other hydrogen which is away from the ring, plane of the ring, these are called the equatorial hydrogens. Okay? You have the 6 equatorial hydrogens, and then you have the 6 axial hydrogens. Okay, so altogether you have the, how many? 12, right? So you have 6 axial, 6 equatorial. You can see the same thing in the picture over here. Like those colored over here. So like say for example this one, the blue, these are axial, right? So you have 6 axial over there, and then the other color, yellowish color, this is going to be the equatorial, going to be away from the ring, right? So once you know that, then we're going to compare the energies when you have the substitution for the hydrogens. Okay? Let's say you have one group substituted for hydrogen. So you have the axial hydrogen, so you have the substitution on that. So this is axial substitution. Right? And you have the other one, this one, so I'm going to write with the different color, so to avoid any confusion, right? So now this one is going to be the equatorial Factorial substitution. Right? When you have that, what's going to be the energy difference? Or you can say from the other words, if you have the same group substitution for the axial hydrogen and for the equatorial hydrogen. So what's going to be the energy difference between these two molecules? So you can say which one going to be more stable than the other one, right? So obviously, if you have the less crowding between the atoms, going to be more stable. Or I can say going to have the less energy. If you have more crowding or hindrance between the molecules, then it's going to have more energy. You're going to say less stable for that. So more energy going to be less stable, less energy going to be more stable. Alright? So now, if you see the axial substitution, you have the overlap some region between the atoms. So atoms going to be close together. So you have the crowding there. You can say the hindrance, the steric hindrance there. So that's going to be unstable. It doesn't want to be that way. You don't want to be relaxed, in which you don't have any atom nearby that's going to crowd together. So it's going to prefer that. So that's going to be the equatorial. So you don't have any overlap over here. So the equatorial is going to be more relaxed. Preferred what? Less energy, more stable. Right? So that's going to be more stable by, if you want to talk about the experimental energy value, this is the value, about 1.8, 1.75, something like that. So that's going to be the energy in kilocalorie per mole stable. What that means? That means the red one over here, the axial, is more energy by 1.7 kilocalorie per mole than the equatorial. That's what it means. Okay? So that's the energy difference. So now, if you think, what about the other groups there? Say ethyl, propyl, butyl, larger than this. Obviously, you can have even more crowding. The energy difference value you have is going to be higher than this. So ethane is going to have more energy difference than methane. Propane is going to have even more than ethane. Because you have more and more atoms there, you're going to have more and more crowding. Right? So if you see the table over here, you're going to see that. Right? So that's the one we saw there. So this is going to be ethane. This is going to be propane, more than that, right? This is going to be butyl, right? So 4 carbons there. So if you see the energy, it's going to go increasing. So larger the group you have for the substitution, you're going to have more and more and more energy difference. Right? If you have the smaller one, say just 1 atom or 2 atoms there, you can see the energy difference less than that. Of course, these are smaller than methyl group. For methyl, you have 1 carbon and 4 hydrogens, so 5 atoms together, right? So here you have less than that. So the smaller the molecule, less number of atoms you have, you're going to have slightly less crowding, so the energy difference is going to be slightly less than the metal. So that's how you're going to see relatively, right? So you don't need to memorize all those values, but just a conceptual difference. Okay? So more group you have there, or larger group you have there, or more number of atoms you have there in the substitution, that's gonna make more energy difference. Okay, that's the one you're gonna remember. You're gonna compare. Alright, so you're gonna have the questions like comparative way, not the individual absolute value you see over there. So larger the molecular group you have substitution, more gonna be the energy difference. Okay, remember that. And also the axial gonna have more energy than the equatorial. So that's the one you're gonna remember. Okay, so now you know the reason why, right? If you have the axial, you're gonna have the atoms or groups very closely packed in one region. That's gonna increase the energy. Okay? Yep.
When you say the energy difference, is it the difference between axial and equatorial?
Yes.
Or the difference between
Yeah, so this is, see over here, axial minus equatorial. So axial gonna have always larger energy, right? So say for example you have 2.4 and then you have say 2.0. So what gonna be the difference? 0.4, right? Something like that. So the difference is the one you see over here. Right, so
comparing to?
yeah, first you're gonna substitute to have the axial substitution, and then take the energy of that, and then do the equatorial substitution, take the energy of that, and then find the difference between that. That's what it is. Right? And also for the different unit, so if you see the second column over there, the same difference but in different units. This is just a unit conversion. So you can see either in kilocalorie or joule, doesn't matter, just the energy difference. Okay? This is like saying yard versus meter or something like that. Just a different unit for the same numerical value. Okay?
Professor,
Yep.
you said that the axial one is always going to have the greater number.
Uh-huh.
So then, just to kind of connect it back to another slide, you mentioned that there's a ring flip, so then the axials become equatorials and equatorials become axials. So then,
No, you're gonna, if you flip that, then you're gonna take the equatorial. It doesn't become axial anymore.
Ah, okay.
It can flip.
Uh-huh.
Okay, so all configurations are possible. So you're gonna take the axial. If you wanna have the energy, do substitution for that.
Uh-huh.
Okay. If you flip to have the equatorial, then do for the equatorial.
Oh,
So focus one you have, and then do the substitution.
okay. Thank
That's
you.
what it means. Alright, so now we're gonna quickly tour functional groups, and then we're gonna go to chapter 4. Okay? So now you have so many different functional groups there. So first, what is functional group? So you briefly touched in that game, right? You have the hydrocarbon at the end of chapter 2 or 3. So you briefly touched over there. Okay? So you have the hydrocarbon. So far, we dealt with alkane, right? So in alkane, you have carbon and hydrogen only. You don't have any other atoms than this, any other element. You don't have oxygen there. You don't have nitrogen. You don't have halogen, right? So just the carbon and hydrogen. So you don't have any functional group there. Now, if you do the substitution, say for example, the simplest one is methane, right? So I'm going to take methane. I'm going to substitute hydrogen by something else. Okay? So let's do OS over there instead of hydrogen. So I'm going to put OS there instead of hydrogen. Then what it's going to be? Now it is functionalized molecule. So you're going to have the functional group. So the group that replaces hydrogen or carbon and hydrogen both. If you have any such group that's going to replace hydrocarbons, then it is called the functional group. So this OH is functional group you have. Okay? So functional group. One example. Doesn't mean that you're gonna have OES functional group all the time. One example. Okay? So how many different types of functional groups are we gonna deal in this class, OChem 1 and in OChem 2? Okay? So these are the groups over here in a sequence. Alright? So the first one, double bond. So you replaced hydrogen, 2 hydrogens from 2 carbons. So if you have alkane, ethane, right? So you don't have any group there. So this is saturated hydrocarbon. So now you're going to replace these 2 hydrogens, you're going to take out from here, right? And then you're going to put the double bond there, right? So alkene, right? So this is the functional group. Double bond is the one who replaced 2 hydrogens there. Okay? So this is one. You can have another 2 pair out from there. So you're going to have the 2 double bond now. Right? So you have triple bonded carbon-carbon in which you have 2 pi bonds there. So this is also different than the first one. Right? So now it is called YNE, alkyne. So the first one was ENE, 1 pi bond there. And then the second has 2 pi bonds, so it has YNE. Okay? And next, suppose you replace hydrogen by halogen. Okay? So now, for the same molecule, I can do this. So you had ethane there. So now I can replace 1 hydrogen by chlorine or fluorine or bromine, any in the halogen group. Okay? So now it is called the alkyl halide or haloalkane. Right? Alkyl halide is going to be the common name. Haloalkane is going to be iodine. Okay? So you have X. So X is the representation of fluorine, chlorine, bromine, iodine, any of these. Okay, so X is the notation for that. You're going to see this all the time in the reaction. So wherever you see X in the organic reaction, that's going to be the halogen. Alright, so it's going to be either fluorine, chlorine, bromine, iodine. So most of the time, we're going to do chlorine and bromine, not fluorine and iodine. The reason is iodine is too fast, reaction is going to be too fast when you use that. Iodine is going to be too slow. So bromine and chlorine are going to be just right for the reaction condition. So you're going to see chlorine or bromine most of the time. Okay? So this is the halogen functional group, right? And then the alcohol, we see in the previous example, right? If I replace hydrogen by OH, if you have that, it is called the alcohol, right? Ether, now what you do is you're gonna put oxygen between the carbon. You're gonna add oxygen between the carbon, so you're gonna have the OCO bond there. So remember, these are sigma bonds. There is no pi bond, no double bond, singly bonded oxygen as a bridge between the carbon, between 2 carbons. If you have that, this is called the ether functional group. That's the name part. Why ether? Well, just put the name and follow that. There is no reason for that. But this is ether. Okay? And then amine. So you're going to have carbon and nitrogen linkage in the molecule, right? So you can think like from ammonia. So you have NH3, right? This is ammonia. So you're going to put hydrocarbon over there. So C, whatever linkage you have there. CS3, C2S5, propyl, butyl, ring, cyclic compound, whatever you have. So if you have that, you have the CN linkage, then you're going to have nitrogen 2 or 1 hydrogen, or you may not have hydrogen, right? So these are amines. Okay? So here you have 2 hydrogens in there. You have 1 hydrogen in the second one. You have no hydrogen, right? No hydrogen on nitrogen. All 3 are amines. So you're going to call different degree of amines. 1 degree, 2 degree, 3 degree amine, right? So now can you guess which going to be 3 degree amine out of these 3? Thus use the concept of 1 degree carbon, 2 degree carbon, 3 degree carbon we went through before, right? If you remember that. So for alkane, you can have a different degree of carbons, 1 through 4. Okay? So here you don't have 4 because you don't have more than 3 bonds there. That's why you can go up to 3. So which is going to be the 3 degree amine? Based on the same concept of carbon, yeah. Which
The
is
bottom one?
bottom one? Yep. So this is 3 degree, this is 2 degree, this is 1 degree. Why? For 1 degree you're going to have 1 carbon nitrogen bond. In 2 degree you're going to have 2 carbon nitrogen bonds. In 3 degree you're going to have 3 carbon nitrogen bonds. That's the reason why. Okay? So these are amines. Anyway, so you have alkene, alkyne, you have the alkyl halide, you have alcohol, you have ether, you have amine, so you have all different functional groups, right? So you're going to have 1 chapter for 1 functional group. Okay? So here we're going to cover alkene, alkyne, and ether, right? So you're going to have more than this. So going forward, after 5th chapter, you're going to have 1 chapter for 1 functional group in an average. Sometimes you're going to have the split for the reaction. You're going to have the same thing for organic too. Right? So we're going to deal these functional groups in detail. All the reactions, properties, everything. Okay? So these are the ones you're going to cover in OChem 2. These set of functional groups. So aldehyde. So this one, if you have the CO group in the molecule, and then you have only 1 carbon in one side, and you have the hydrogen in the other side. So this is a must. If you have that, that's the aldehyde. Okay? And ketone is very similar to this. So both are called carbonyl compounds, the same name. The difference is this one. So you have CO double bond like aldehyde, but you don't have any CH bond over here. No CH bond. No carbonyl CH, not the other carbon. You're going to have other carbons on the other side. So you don't have any hydrogen with the carbon that has the carbon-oxygen double bond for that carbon. Okay? If you have that, this is called ketone. So the only difference between aldehyde and ketone is the hydrogen bonded to double bonded carbon. For aldehyde, you have hydrogen there. For ketone, you don't have hydrogen. That's the difference. Okay? So the difference is this one. This and this. That's the difference. Right? And then carboxylic. This is also carbonyl compound plus other functional group. Actually, it has two functional groups, you can think that way. So this is one CO like, no, this one. CO like aldehyde or ketone. You have CO double bond there. Okay? And also you have the alcohol functional group there. You have two functional groups. One carbon oxygen double bond, and then other is alcohol. If you have that, this is called carboxylic acid. So these are going to be anything, methyl, ethyl, propyl, butyl, ring, whatever you have. As long as you have the CO double bond and OH on the same double bonded carbon. If you have that, that's the carboxylic group. Right? That's the carboxylic functional group. And ester. So now, instead of alcohol, you're going to have the OR there. So you're going to have COC linkage, and also you have the CO double bond there. Right? So most of the time, you may be confused with ester and ether. Remember the one we discovered in the previous slide? Ether and ester. Seems like similar. Right? The difference is ether does not have double bonded carbon. Right? So ether, let me write over here. So ether does not have CO. Right? So it has another part. So you have this in ether, but not the double bonded carbon oxygen. You don't have that. But in ester, you have double bonded CO. That's the difference. Okay? And the other one is amide. So let me compare this first, and then I'm going to go back to acid chloride. Okay? So for amide, so we see amine before. In the previous slide, you have the amine functional group, in which you're going to have the C and N bond, right? That's the amine. Amide. So here you have this. Still you have CN like amine. So amide is amine with additional CO double bond there. That's the difference, right? So amine does not have double bonded CO there, but it only has CN single bond, right? So the common is this. So the common on those is CN single bond and CN single bond. So this is common for both, but double bond is in amide, not in amine. Okay? So it is very confusing. So maybe confused like first when you see these functional groups, but when you are used to, it's not that hard. Okay? Acid chloride. Oh, there is a typo over here. So this is not. If you have RCl, that's alkyl halide, right? So you see the previous slide. So you're going to have the CO, and then you have the halide group, right? So you have the double bonded carbon, and then you have the chloride there, in particular, because it is acid chloride. If you have bromide, it is called acid bromide, okay? And hydride. So it is the specific compound found by the dehydration of acid. You have the bridge. You have the oxygen bridge between two carbonyl. So you have the CO double bond left and right, and you have the oxygen bridging these two groups. So this is called the anhydride. Sometimes it is called acid anhydride. The reason is you're going to make this from the carboxylic acid. So you're going to dehydrate, you're going to remove the water molecule out from there, and then you're going to have this compound. So it is anhydride without water. Acid anhydride because we make these from carboxylic acid. Alright? So these are functional groups. So nitrile imine phosphate, you have addition of these. So we're gonna cover all these in OChem 2. So these three and then all these functional groups. You're gonna have one chapter for one functional group, you're gonna go in detail reaction, mechanism, everything like that. Okay? So with that, this chapter is done. So make sure you are familiar with this, the first one, first slide. Yep.
So then how would you name it, like if you have an alkane connected to it?
Yeah, we're gonna do nomenclature too.
Oh, okay.
So for each chapter, you're gonna do the nomenclature, reaction, everything.
Oh, okay.
We're gonna do it.
Yeah.
Yep.
Are you going to be tested on any of those?
Mm-hmm.
Are you going to be tested on any of those in the 7 months?
Yes, you're gonna have from the. If you focus on these, you should be good. But make sure you know these too. All right.
Will those be on the exam as well?
Yeah, for the exam, I'm gonna give you from this slide, but be also familiar with these. Okay. Good. All right. Oops. Now we're gonna go to chapter 4. In this chapter, we're going to do acid and base, and the equilibrium a little bit to have the equilibrium constant. So, kind of review of Genchem you have Genchem 1 and Genchem 2, right? So now, acid and base. How do you define that? In the qualitative way, you can say you can distinguish from the test. Okay, say litmus test, right? So the red litmus to blue or blue litmus to red. Based on that, you're gonna say acid and base, right? But if you wanna see the theory behind that, we have mainly 3 theories that are gonna define acid and base and their reactions. Okay? So the first one is Arrhenius theory. So this is the first theory introduced to define acid and base and apply to the chemical reactions. Right? So in chemistry, whenever you say acid base, we're gonna see that in terms of reaction. Right? So this theory says that any compound, right? If you want to define whether it is acid or base, what you need to do is you're going to take water in a beaker, for example, and then you're going to put that compound there, right? And then see what's going to happen. That's how you're going to define acid or base, right? So the specific criteria for any compound to be acid is when you dissolve in water. So water is the specific solvent, remember, not on other solvent, only in water. Right? So water is specific for this theory. When you dissolve that, if that compound gives H plus ion there, it is acid. If it does not, then it is not acid. That's how you're going to define. Right? So, of course, you're going to have a lot of limitations of that. Not all compound or not all acid going to give proton or hydrogen. you have acids that does not have hydrogen in their formula. They cannot give. Right? So you have limitations on that. But if you focus only this theory, you're gonna say when it dissolves in water, it has to give S plus or the hydrogen ion or proton, whatever you call, right? So for S plus, you're gonna call proton because it has only one proton, it doesn't have electron there, so it is proton, right? Or hydrogen ion or S plus ion, same thing, okay? So sometimes for this, you're gonna write S3O plus hydronium ion. Both are same thing, right? So for S3O, you're gonna have water molecule there, right? You are dissolving water. So this S plus is attached to the oxygen, like this. So this is S3O plus, right? Because hydrogen doesn't have electron, so the bond is formed by lone pair of oxygen. So it is plus, electron deficient molecule, right? So that is going to become ion. So hydronium ion. You're going to write it this way, or you can write HCl. You're going to write H plus, Cl minus, same thing. Whatever way you're going to write. Okay? So these are the aqueous medium. Always, this is aqueous. That is in water. Okay? So that's the shape. What about the base? So the same thing. Water is must. You're going to have water. And you're going to dissolve the compound. If you want to see whether it is base or not. If that compound is going to give OH minus, that's going to be the base. If not, this is not base. Right? So that's the simplest way of defining acid base. Right? Of course, not all compounds going to have hydrogen, not all acids going to have hydrogen, not all base going to have OH. Right? So what going to be example? Say AlCl3, this is acid. You don't have hydrogen there, right? Say NH3, ammonia, we know it is base. It doesn't have OH in the formula there, so you cannot define all based on that, okay? But this is how you're going to define. Now the second theory is Bronsted-Lowry theory. So it also going to define kind of like a similar way, but it does not require water. So the condition that water has to be there to dissolve is taken out. Water is not required. Okay? So this is going to be the reaction specific. So you're going to take two compounds, you're going to react that, you're going to have the product. So by comparing product and reactant, you can define which is acid, which is base. Right? Water is not must over here. That's the improvement over previous theory. Okay? Let's see. The same previous example. You dissolve HCl to water, and then you're going to have the H3O there, and you're going to have the Cl minus there. Right? That's the reaction. So now, you're going to see over here which is acid, which is base. So, if any compound that's going to donate proton, right? Donate as plus. So proton donor. If you have that, this is acid. Okay? That's how you're gonna define it. Acid is proton donor in the reaction. Again. Okay? And the other one, which gonna accept the proton. So proton acceptor. So this is gonna be base, right? So that's how you're gonna define it. So OH requirement is not there. So one gonna give proton, other gonna take that proton, right? So whichever takes the proton, it is proton acceptor, that's the base. Whichever gonna give the proton, which is proton donor, that's the acid. That's how you're gonna define. Okay? So the another reaction you have here, there is no water. So no water as a requirement like previous theory. So you're gonna simply see reaction. So find out which is proton donor over here. Is it HCl or CH3OH? So CH3OH is a methanol. So out of methanol or the hydrochloric acid, which is proton donor? So it is proton donor because after donating in the product, you don't have proton there. You have only Cl minus. So proton is donated to other molecule. So methanol now becomes one extra hydrogen there. Right? So the methanol is proton acceptor. So now you know which is acid, which is base. Right? Hydrochloric acid is acid because it is proton donor. And methanol is base because it accepts the proton given by HCl. Right? So one thing you need to be very clear over here is that these acid base are relative. It doesn't mean that methanol is going to be base all the time. This is the reaction specific. In other reaction, methanol can be acid. Okay? If you have any reaction that methanol is going to give proton to the other one, at that condition methanol is going to be acid. So based on this theory, acid and base concept is the reaction specific. So take the reaction, whatever you want to see, and then define based on that. Okay? It doesn't mean that whatever you say acid based on this theory is going to be acid all the time. No. This is reaction specific. Okay? So now you know base, right? So if you see the other one over here, so CH3OH, so which is the proton donor? This is proton donor, right? So now it is proton donor. So this is base. Sorry, acid, right? And the OH minus. So you're gonna have the OH, one extra H on that. So this is base. Right? So now if you compare these two reactions, in previous reaction, methanol, it was acid. Now, in the second reaction, methanol is acid now, base, right? Acid or base? Acid. So here it is base. Over here it is acid. See? It is different in different reactions. The reaction is specific. So take the reaction, see whether donor or acceptor. If donor, acid. If acceptor, base. You have to define this way. Good? Any confusion on that?
Yes, I do have a question. So is there a reason why for the Bronsted-Lowry base, the H2O is written with the H in front of the OH instead of like...
No, there is just a aqueous solution. So whenever you have the solution, You can write Na plus AQ, OH minus AQ. This is dissolved in solution phase.
Okay.
You're going to have NaOH solution in one test tube, and then you're going to have the methanol in another test tube, and then you mix them like that.
Alright, thank you.
All right. All right, so now here, so these are the types you're going to have the question in the exam. Okay? So also in the final exam, most probably. So you're going to know what is conjugate acid and conjugate base. So before that, you need to identify which is acid, which is base. Now we can do that. Based on that, you're going to say the conjugate acid of a base and conjugate base of acid. So you're going to select the pair. So the conjugate acid base pair is going to be always between two. So here, this is one pair, this reaction, and then you have the another pair. Right? So if you see first one, what is the relation between them? So HCl, you have hydrogen there. It's gonna donate hydrogen, and then the remaining is without hydrogen over here. You have Cl minus, no hydrogen on the right. Okay? So the first one was acid because it donates proton, right? And after it gives proton out, whatever remaining you have, which is Cl minus, that's going to be the conjugate base. So conjugate base, right? So it's over here. So HCl is going to be acid, and then after it gives proton out, remaining going to be Cl minus. That's going to be conjugate base of acid HCl. Okay, and then the other one is going to be water. It is base because it's going to accept proton given by HCl. So now what is the product when it gains proton? So you're going to have one extra hydrogen in water, right? So that's the extra hydrogen gained from HCl. So this is conjugate acid of the base water, right? So now if you see the HCl and Cl minus, so this is going to be one conjugate acid base pair, and then water and hydronium ion is going to be another conjugate acid base pair. You have two pairs over here, two conjugate acid base pair, right? Now the thing you need to be careful is normally whatever you have the acid base pair on the left side, so you're going to call them simply acid or base based on their nature. Okay? Whatever you have on the right side, so you're going to call the conjugate for that. Conjugate acid or a base based on the nature. So the conjugate is for those product you have after the reaction. Acid and base without any conjugate there. Just acid and base going to be for the reactant on the left side. Okay? That's how you're going to name them. So, if you see the another example, actually it's the same, right? Let's see whether you have more example over there. Okay, that's a good one. So now, you have different examples over here. So acid, if you have the H3O plus acid, then what gonna be the conjugated base of that?
H2O.
So why you gonna have H2O, not OH minus, for example?
Oh, because it only donates one at a time.
Yes. So remember, it is relative, right? So from here, you have H. Let me hold it down. So you have the H, and then you have S, right? So if you remove one hydrogen, this is remaining. So that's a conjugated base, obviously, right? Make sure review all these examples. And if you have any questions, let me know. Right?